So good afternoon, colleagues. Today is the third day of our school. Welcome back. I hope you all could follow. And we start today a bit later than normal because we want to accommodate our speakers from Canada so that they wouldn't be forced to wake up at 6 o'clock in the morning. But we start with the lecture from Dr. Ross Woods, reader in Water and Environmental Engineering in University of Bristol. He, however, is originating from New Zealand. However, I know his family is coming from UK initially. He graduated from University of Canterbury with degrees in mathematics and operations research. So traditionally we have, as always, a lecture 45 minutes plus 15 minutes for questions. And I would like also to welcome everybody on behalf of Professor Gelfand, who is co-chair of this school and director of the Institute for Water Problems of the Russian Academy of Sciences. And I would like to acknowledge the Russian Science Foundation for providing partial financial support to organize this school. So, Dr. Woods, floor is yours.
Thank you very much. Can you confirm for me, please, that you can see my slides?
Yes, we can see your slides on the Zoom, and I hope they will be also seen in YouTube when the broadcast starts. Yeah.
Thank you. Okay. So, first of all, thank you very much for the invitation to be here. It's an honor to be asked, and I'm really looking forward to telling you about some of the work that I've been doing with my colleagues to try to use ideas of classification and similarity to better understand global hydrological processes. So the centerpiece of the work that I'll present today is work that I've done with my colleague Lena Stein, but it also involves the work of many other colleagues, both at Bristol and at other universities as well. And so I've acknowledged them on my opening slide. Just in case you don't know where Bristol is, there's a map of Northwestern and Central Europe, and you can see Bristol marked on the map there, and a little bit about where I was before I was in Bristol and where I'm from. So I'm from New Zealand. I spent about 25 years working in New Zealand as a hydrologist. I did a PhD in Western Australia with Siva Sivapalan, and then moved to Bristol in 2013, where we have a large hydrology research team in both civil engineering and geographical sciences. If I was to say what sort of hydrologist I am, I think I've been through several different stages. I went through a stage of doing a lot of field research, and then a stage of quite intensive modeling. And now I try to spend a bit more time with data and thinking about what the meaning of data is. So I've had a number of different perspectives on hydrology. Today I want to talk to you about something that's been a passion of mine for about 25 years, and that is the idea that in hydrology we might adopt some kind of common classification system which we could all use. And I will come back to ideas about how we might use that at the end of the talk. But today, I want to first outline for you a proposal for how we might do this classification, whether it actually works, whether we can achieve anything with this, that we can go beyond just putting things in little boxes with labels on them and actually put this classification to work. And then I'll talk a little bit towards the end about what else needs to be done, what other opportunities there are to go further in this work. So here's my proposal for how we might classify and organize in hydrology. Suppose that you learned something through detailed field study at a few sites. And then you might wonder to yourself, where else does that result apply? Where else can I use this piece of knowledge? Imagine a world where you knew which places were similar to yours. That's my dream. That's where I would like us to get to one day. One way of thinking about this and how to get there is to break the world into three kinds of places for the point of view of hydrology. And those three different places, water is stored predominantly in different states. So in one of those places, water is stored in pores. So typically there will be soil water or groundwater. The second type of place, water is stored in frozen form. So this will be glaciers and snowpacks, typically. And the third form is open water bodies. So these are lakes and wetlands, for example. The reason for doing this is that the forces that lead water to be stored or to leave these three different settings are quite different. What it takes to unfreeze water is quite different than what it takes to get water to flow out of a lake or to drain from a soil. And so this was my idea in sort of analogy with solids, liquids, and gases, that we might have in hydrology different dominant states of stored water, and then we'd have domain-specific knowledge that was relevant to each of those types of storage, maybe in the same kind of way that in fluid mechanics, we have different descriptions of flow for turbulent flow systems compared to laminar flow systems. If we know that we have flow which is laminar, for example, then we have a different way of describing it than if it was turbulent. It's still the same underlying fluid, it's just operating in a different regime. And my hope is that one day we might develop the same kind of thing for hydrology. This seems like a very ambitious thing to do, so you might wonder where to begin. So I decided to start with a few simple hypotheses that might explain some obvious patterns that we see, and then exploit a very small amount of process knowledge about how systems work. So what happens in a hydrological system where water is predominantly stored in and released from pores, or stored in and released from a snowpack? My approach is not to get caught up in complexity, but just try to explain a few simple things at first. And my motivation for doing this is scientific understanding and not catchment management or water management. If I was doing it for those reasons, then I would have done this a very different way indeed. From a more practical point of view, my approach is to choose a particular time and space scale and then expand to other time scales and space scales. And I've chosen to start mostly with annual and seasonal cycles and without spatial complexity. And I just did that because it was easier. This isn't the only way that you could try to solve this problem. It's just the choice that I happen to make. And it might be that the real solution actually lies somewhere else, but this is what I'm trying. My inspiration for this comes from a fantastic piece of work by Falkenmark and Chapman called Comparative Hydrology, which attempts to describe the hydrological processes and hydrological balances of many different hydrological environments around the world. And I think really this was a very trailblazing piece of work, and there's still a lot that we could do with an approach like this. What I've done is I've started with a climate classification for hydrology. So not trying to do everything about hydrology, but just saying, what are the different kinds of climates from the perspective of a hydrologist? And what do we need to describe which climate we are in? Now, it might be that if I was a plant physiologist, then I would have quite different ideas about what aspects of climate were important, but we tried to think of it from a climate point of view and identified 3 climate variables that at the scale of the globe were useful. 1 to describe aridity, 1 for seasonality, and 1 for the snow fraction. And here's an example of that applied to the USA. You can see here, at the moment, I'm just showing you what would happen if we calculated some indices that describe these 3 things. An index for aridity, which shows that the places with a low aridity index, these are relatively wet places, are colored here in red and over here, and the dry places are in the center. In this case, we're describing seasonality by something that describes whether the precipitation falls during the cold part of the year predominantly. So over here in Mediterranean climates and in the Northwest, most of the precipitation falls at during the cold part of the year, but in other places, precipitation is dominantly in the warm season. And this can make an important difference to hydrological outcomes. And finally, a measure of the fraction of precipitation falling as snow, because if precipitation falls as snow, then it goes into a snowpack, and then you have to wait quite some time for it to come out again. So the fate of water and the hydrological processes that are active can be very different if any one of these 3 indices is different. Using these indices, we were able to separate the hydrology in the UK into about 10 different classes, which made sense from a climate point of view, that climate was quite useful at breaking the US up into different kinds of hydrological behaviors. And if you look at the references at the end, you can read much more about this. I don't want to go into it in a lot of detail now. What we did do next was we said, having had some success in grouping the hydrology of the US into coherent groups just using climate, we said, now let's try this at the global scale. So once again, we used the same kinds of ideas, that we would have a metric for, on average, is the catchment or the location we're interested in, is it water limited or energy limited? Then we would find some metric to say, what is the range of aridity within the year? So is there a part of the year which is very dry and another part which is very wet, so that we have a strong seasonal cycle and water availability? Or is this a place where the water supply the net water supply stays fairly consistent through the year? And the third metric we used again was how much precipitation falls as snow. If you're interested in looking into this and trying to make sense of this a little bit more, you might find these pictures helpful, maybe, but I'm not going to spend too much time on them now. I just wanted to get across the idea that we might have a climate which was wet. The top row, so both of these climates, the blue line on average is above the red line. That means precipitation exceeds evaporation throughout the year in this cartoon. And in both of these top pictures, precipitation exceeds evaporation, but in one of them, the difference between precipitation and evaporation is constant through the year. And in the other one, the difference between precipitation and evaporation fluctuates strongly through the year. So we have a pronounced wet season and dry season. So we can have either pronounced wet and dry seasons or consistent wet all year round, depending on within year variability of the climate. So that's what these aridity and seasonality metrics are designed to measure. Now, what does that look like for the whole world? So here first is this metric for aridity. I'm not going to go into the details of how we calculated it. You can read about that in the paper by Wouter Knoben. But basically, if you see places on the map that are light colored, in terms light red, then these are relatively wet places, and the dark is relatively dry places. We can also look at seasonality. So on this map again, if you look at the dark places, these are places that are strongly seasonal. there is a big difference between one part of the year and another part of the year, so it switches from dry to wet. Whereas if it's very light green, that means that there's not much change during the year. It might be that it's very wet all year or very dry all year, but the seasonality indicator just says doesn't change very much. And the third one is the fraction of precipitation that falls as snow. Now, if you want to try to synthesize all of this and put these three indices together, you can do that. You can make a three-dimensional picture. So you could have, for every point on the planet, an axis for aridity, an axis for seasonality, and an axis for snow fraction. And you can even combine all of the colors so that at every point you can say the color at this point is a mixture of the amount of red that the aridity signal tells us, the amount of green that the seasonality signal tells us, and the amount of blue that the snow fraction signal tells us. And since I'm being hosted by an event in Russia, I thought I would follow this up with a zoom onto Russia so that you can see, according to the global climate data that we had, you can see the more strongly snow-dominated regions in the far north and the far east. You can see fairly strong seasonality over most of the country, except maybe for some regions in the southeast. And you can see a mixture from more arid to drier regions, depending on which part of Russia you were in. One of the things we then did with this climate information was we grouped hydrological data from all around the world into classes according to the mixtures of aridity, seasonality, and snow fraction. So if you look at this little three-dimensional picture at the bottom, we've got 17 dots on this page, and these represent 17 different climate classes. And then we plotted river flow data for each of these 17 classes. And what we found was that river flows that were within the same climate class tended to be quite similar to one another, and river flows that belonged to different climate classes tended to be quite different to one another. We tested this against the standard climate classification technique that's used globally, which is the Köppen-Geiger classification. And what we found was that this new classification outperforms Köppen-Geiger, particularly in cold climates. So if you've been doing work on the hydrology of cold climates and finding that your climate classification isn't doing the job you wanted to, maybe you should have a look at this one. Okay, we wanted to go beyond what's often described as the Boudico curve, which is a relationship between the aridity and the evaporative fraction or the runoff fraction. So we wanted to also look at impacts of seasonality of climate on runoff and snow fraction effects on runoff. I don't have enough time to talk in detail about all of these, but I will show you a couple of examples, and I've left a reference to a paper that we published a few years ago on the impacts of snow fraction, the very significant impacts that snow fraction changes in snow fraction have on stream flow. I think the main point that I'd like to make in all of this is that there's a tendency in research at the moment to plot data points in this Boudico plane, aridity versus evaporative fraction, and to fit curves to those points. And I'd really encourage anyone who's interested in this field to start thinking about process explanations for why points plot in different places on this field. So here's an example of a Boudico curve. Here's evaporative aridity index along the bottom, mean potential evaporation over mean precipitation. These are the wet catchments over here. These are the dry ones over here. And this is evaporation divided by precipitation. And what you can see is I've colored these points in according to that three-dimensional climate descriptor. And you can see there's a bunch of bluish looking points which are down here that are quite different to the brown and green ones up the top. And what that means is for the same aridity, we are getting different long-term water balance depending on the climate. When I say depending on the climate, I don't mean depending on aridity. Aridity is fixed. It's some other aspects of climate which are important. And so that example on the left, these are 559 catchments in the US. Another way of looking at this is to plot the points in our three-dimensional climate space, aridity, seasonality, and snow fraction, and use color to represent the runoff, the long-term runoff ratio. And the blue dots are catchments where the runoff ratio is low, and the yellow dots it's high. And what we find is that if we travel along any of these axes, along the aridity axis, or along the snow axis, or along the seasonality axis, in all cases, it makes a difference to the long-term runoff. So I think we should be including more variables than just aridity when we try to think about explaining long-term runoff. I think in the interests of time, I am going to skip this very beautiful picture, but this is telling the same kind of story, but instead at a global scale. Okay. Now, one of the things that I wanted to do was to stop thinking just about long-term runoff and seasonality, but also to start thinking about floods. One moment, please.
Hi, I'm Lena Stein. So we just saw that we can connect climate to the flood hydrograph and to runoff processes. So then we should be able to do this the other way around as well. We should look at the processes and be able to connect this to climate. And now that we're looking at floods, we first need to identify, well, what are the processes that we see with floods? And for that, we developed a classification tree that identifies 5 different flood generating processes. So we either look at the connection between, so we see one process would be, for example, the combination of rain and snow. That would be the very top, or we just look, is there enough snow melt to cause a flood event? And then another process would be excess rain floods, where you have a saturated soil and you don't need very high rainfall amounts for that to actually cause a flood event, because the soil is saturated, you get a lot of runoff quite immediately. But if the soil is quite dry, you need extreme rainfall amounts, and you can either have a short concentrated rainfall on one day, which would here simply call short rain flood, or over several days, and that would be then a long rain flood. If none of those processes are identifiable in the weather before a flood event, we would just say, okay, then we don't know what it is. It might be a dam break, it might be an ice jam, but this is not something we can classify as a hydrometeorological process. So now that we have this classification tree, we can look at the single catchment and classify, for example, for the annual maximum flow event, classify the process. And as we can see here in this time series for the Meidzin River, which is in Russia, that this one is quite snowmelt dominated. We can see quite a few snowmelt events, which are in purple here, interrupted by a few combinations of rain and snow, and a few excess rainfall events, so rain falling on saturated soils. So what we can take home from this one is we have multiple flood generating processes within one catchment. So assuming that you have, for example, a flood frequency curve, assuming that they're all from the same distribution, you should take into account that this might not always be the case. So if we look at a single catchment, that's what we learned from the single catchment. But since Ross was saying we like looking at patterns, we also want to look at the whole world. or wherever we have data. And when we look at just the dominant process, we can see that there are quite a few catchments that are dominated by excess rainfall events, particularly in the tropics and in Europe. Most flood events in those catchments are caused by rain falling on saturated soils. Then in the higher regions or higher latitudes or in mountainous regions, we see a few which are dominated by snowmelt events. And then, for example, in Southern Africa and in the US, there are quite a few catchments dominated by long or short rain flood events. So more extreme rainfall events, which are causing the flood processes. So excess rainfall is an important process. That's the take-home message that we can see from this picture. But in terms of the patterns that we see, does climate influence the processes? Well, we can see quite easily there is a change, for example, in the US, along the aridity gradient that we can see there. So on the left is a rainfall map of the US, and on the right are the flood processes. And we can see that the change from excess rainfall dominant catchments to more short rain or long rain dominant catchments occurs mostly along the aridity or gradient. So in more arid catchments, are more dominated by short or long rain floods and not by excess rainfall. Well, does only climate influence those processes? Is it completely, does it not matter what, for example, the catchment area is or the slope or what kind of soils or vegetation you have? Well, that's the next step we wanted to evaluate. And here we're making use of the CAMELS dataset. The CAMELS dataset is a dataset of around 600 catchments in the United States, which have both hydroclimatic data, a time series, and catchment attributes available. So exactly what we're interested in. Since we already saw before that aridity and also snow availability are quite important climate indicators, we split this data set into 3 different climate types that we very simplified called as wet, dry, and snowy areas. So we can compare the influence for the different attributes in those regions. So what are the attributes that we can test which are available in the CAMELS dataset? So broadly speaking, we have topography attributes, for example, slope, elevation, area. We have climate attributes, which include the ones that Ross mentioned before. So we have precipitation seasonality, aridity, fraction of precipitation falling as snow. We have soil data, so for example, porosity and conductivity, soil depth. And we have vegetation attributes, for example, leaf area index or forest fraction. And we have geology attributes, so that would be subsurface permeability, for example. So how do we actually evaluate what the influence for each of those attributes are? Well, we're gonna use we did use a random forest model and evaluated the influence of each attribute using interpretable machine learning method. I'm not going to go into the details here. If you want to read more, we have this paper under review at the moment, and you can look at the preprint that we submitted. So, but the thing that you need to know is that basically the darker the point is, the more influential is the attribute. And the larger the point is, the more we actually trust the result that we're seeing. And on the bottom, you can see our different processes. And in general, we can see, oh yeah, it's definitely the climate attributes which are mostly the important ones. They're important for nearly all flood generating processes. They're important in all the different climate groups. But it's not always the same one for each process, and it's not the same ones in the wet, dry, and snowy catchments. For example, in snowy catchments, elevation is also a very important attribute. So the takeaway message for this one is that you need to take into account what process you're looking into, and you need to take into account what climatic area you're looking into to actually evaluate the influence for the different attributes. So what are the implications for that? Why do we do this? For example, if you're looking at the effects of climate change, you might want to evaluate this separate by different flood generating processes or separate by different climates, because the impact of climate change might differ between the different climates or the different processes. Especially, for example, snowmelt influenced flood events. They can already see that the snowmelt influenced flood events are changing more towards rain and snow floods. But maybe John Pomeroy will later talk to you more about snowmelt influenced catchments. So to summarize, there are multiple flood generating processes that can occur within one catchment. And it's quite common that you have multiple processes within one catchment. Excess rainfall is a widespread flood generating process. So soil moisture is quite important in flood generation. The more arid a catchment gets, the more it's dominated by extreme rainfall events, either over one day or over several days, as opposed to soil moisture. And climate attributes are influential in all different climates, but other attributes are importance depends very much on the climate type. So thank you.
So the long game with this, where we are going with this research, is eventually to be able to say, anywhere in the world, what types of floods do we get in this kind of place? What types of floods do we expect here? And then from that knowledge, can we say, how sensitive are the flood magnitudes in this place to potential changes? Ultimately, we would like to go to being able to do process-based flood estimation based on this kind of information. But that, I think, that goal is still 1 or 2 PhDs away into the future. Okay. Having finished talking about floods, I wanted to also talk a little bit about more stable seasonal flows, the seasonal phase and amplitude of stream flow. And this gives us an opportunity to look at how climate and geology interact. This is work by my colleague Sebastian Genan, and he's been looking at seasonal damping and phase shift of climate signals in places where rainfall and evaporation are dominant processes. So snow is not particularly important in the places that Sebastian has been studying so far, and most of the places are not especially dry. So he's been looking at, now if we look on the left here, we can see a signal calculated with daily values for about 10 years of precipitation minus potential evaporation. So these gray lines here, these are the daily values, and the blue sine curve here, this is the seasonal cycle of P minus PET. And you can see that it goes up and down with a certain amplitude. And below it, we've got plotted the stream flow. And we've also fitted a sine curve to the stream flow as well, so that we can represent the seasonal cycle of the stream flow. And then on this bottom graph, we've just normalized them, well, not normalized them, put them both on the same scale so that they're easy to compare. And what you can see in this catchment on the left is that the seasonal fluctuations in net input, precipitation minus potential evaporation, are very similar to the cycles in stream flow seasonality. Whereas in the other one on the right here, the precipitation minus evaporation is quite similar, about the same amplitude, but the stream flow response is much more damped and delayed. And when we saw this, we thought it would be interesting to try and characterize seasonal catchment response. So this is another time scale that we're interested in, the seasonal catchment response of different catchments and to see whether we could explain what was going on. So we've plotted here for the catchments that we've studied in the UK, along the x-axis, something we call the amplitude ratio. So this is the ratio between, if I go back to this picture again, it's the ratio between the amplitude of the blue curve and the amplitude of the orange curve. So in this case, because there's not much damping at all, the amplitude ratio is almost 1. Over here on the right, the amplitude ratio is much smaller. So we plot here on the x-axis for each catchment, its amplitude ratio, and on the y-axis, its phase shift. So how long is the delay between the peak of the net forcing and the peak of the seasonal stream flow? And what we found was a tendency for very small phase shifts in the places that had a low, an amplitude ratio close to 1, and generally longer phase shifts for the places where the response was much more damped. And then we thought about, if you look at any particular amplitude ratio, there's quite a range of different phase shifts. Sometimes you can have a lot of damping without much delay. Sometimes you have the same amount of damping and a lot of delay. And we wondered why that was. So we colored in the catchments according to a measure of their climate aridity. So the pale colored ones in this picture on the left, the pale ones are the wet catchments, and the slightly darker ones are the somewhat drier catchments. But because this is the UK, none of it's really very dry. And what we saw was there was a tendency for the slightly drier catchments to have the smaller amplitude ratios, but it wasn't particularly strong. But what we found when we looked at the percent of fractured aquifers was that it was the presence of fractured aquifers was having a big impact on the amount of phase shift. So these fractured aquifers are not necessarily altering the amount of damping that's going on, but they are having a big effect on how long the delay is between the peak of the net forcing and the peak of the stream flow. We did the same kind of analysis in the US and found that the climate controls were kind of similar, that the wetter catchments tended to have smaller phase shifts and smaller amplitude ratios, but we weren't really able to learn very much about the impacts of geology in the US. This is a problem that Sebastian is still working on, and he's recently submitted a paper to Water Resources Research where we try and do a follow-up study on getting a better understanding of the role of geology in controlling streamflow regimes. So, where are we going next with this kind of work? So I've talked about 3 different examples, one for long-term, for mean flows, for floods, and for the seasonal cycle of flows. There's still quite a lot more that could be done with this framework. Things that are missing from here are a lot of catchment descriptors. There's lots of, we don't really have a good descriptor for hydrogeology, but we know that in some places, including hydrogeology is very important. And there are a number of other variables related to other processes in the hydrological cycle which seem likely to be important, but we don't really know exactly what it is we're going to need. So I have a bunch of ideas I could try, but I'm not quite sure what's going to work. One of the largest gaps is in places which are dominated by lakes and wetlands. I haven't really started working on this except to recognize that they're different and that some interesting work has been done by a bunch of other people that I don't yet know very much about. We also have the potential to do estimates for quantities such as flood magnitude or alternatively low flow statistics using this kind of knowledge, but there's quite some way to go there yet. I think there's also potential to link this approach to work that other people have already done, which is highly relevant, but doesn't necessarily include the seasonal emphasis that we've put into this work. So the work that Ignacio Rodriguez Iturbe and more recently Gianluca Botta and his colleagues have done on stochastic dynamic modeling of soil moisture, I think there's definitely opportunities to link that with the sort of work that we've been doing here. I think there's also interesting opportunities to link what Sebastian Ganan has done on seasonal hydraulic response to the work that Jim Kirchner has done on seasonal tracer response. It seems to me that there's really a lot of potential if we compare those two. They ought to be different, but they ought to be somehow connected as well. And so I think that's possibly a promising direction for the future as well. And as I said, lots of work still to do on open water bodies. But in the interests of time, I don't want to spend much more on that. I wanted to talk more about why am I doing all of this? So not so much how to do it, but where is it going? I think one of the things I hope that this work will lead to is improved communication between people who study hydrology in different geographic locations, that we can describe what kind of place we're working in much more clearly than saying, oh, I work in a mild temperate catchment or a maritime forested catchment or a steep, thin soiled catchment, that we could have some kind of consistent way of describing to one another what sort of place we're working in. I would hope that the type of results we're generating would allow people to create new testable hypotheses to say, well, I learned something by detailed study of this particular place, and with these similarity indices, I can identify lots of other places that ought to be similar to the place that I've studied in detail. And then we can see, are those places actually similar? This is also a way that we could enable meta-analyses where we compile together and study experimental data from many different, geographically different places that should be similar according to the similarity variables we uncover here. It's also potentially a way to design better monitoring networks, to make better use of data that other people have collected, because we'll know whether their data is from places that are similar to ours or not, and enable us to do more rational transfer of information from one place to another. And ultimately, if I was to continue the dream, I'd hope for a classification section in every textbook, chapter 1 of every hydrology textbook, classification section that we could generally agree on, that we could use as part of our common language and teach to our students and use it in journals and talks and proposals, so that we were clear what we were talking about and we were able to link our work to other people's work. Now, I recognize that adopting a classification system like this is really a social decision. It's not really a purely rational thing. It's not fully evidence-based whether we should use one classification system or another. But for it to be successful and for, as a group, for hydrology to take something like this on, it needs a broad audience. So lots of people need to be interested in this for it to be useful. It needs to be well marketed, and that's not really my personal skill. It needs some fantastic examples that make it really, really clear that we can identify places that you might have thought were different, but are actually the same. And it needs to be useful. We need to be able to actually do something with it. So, thank you very much for your time. There's a list of references there at the end if you're interested in reading more about this, and I'd be very happy to take any questions.
Dr. Ross, thank you very, very much for this really interesting and thought-provoking presentation. Right, now we take a breath and we move to questions. May I suggest that so that audience can see you, maybe you could click on the button stop presentation on top of Zoom. There's a red thing, stop sharing screen. Excellent. Yes, now everybody will be able to see you when you will be answering questions. I liked especially this social aspect of classification. That's interesting idea. I never thought about this. We need maybe to think more about, in general, how in science this classification could be driven actually by social values or perhaps social pressures. Right, but we go to questions from the audience, and we have a number of questions collected here. So I will be posing question to you. You cannot see it, in principle, you can see it in live broadcast in the YouTube channel, but there is a certain delay, so maybe not all questions are seen at the moment. So the first question is from Dr. Vsevolod Mareido of the Institute for Water Problems. His question is this: by excess rainfall, do you mean excess over soil water holding capacity? That's first part. And second, how do you classify if, for instance, 3 small rain events individually don't lead to flooding, yet the 4th small event, rainfall event, does? Ross, could you yes.
Yeah, that's
unmute.
okay.
Yeah, yes.
So to answer the first question, yes, we define excess rainfall as the rain which exceeds the soil water holding capacity. And the second question?
It was about 3 small events that don't individually lead to flood, but the 4th one does. How do you classify?
But the 4th one does. So the event, the process, the method that we use to identify and classify events does keep a running total of how the soil moisture is becoming wetter and wetter. So the first 3 events will increase the soil moisture more and more and more. And if that was sufficient to fill the soil or almost fill the soil, then the 4th one would be counted as a rainfall excess event. And the other 3 would not, because there was still space in the soil to hold the water.
Okay, thank you very much. We'll move to the second question. Professor Woods, yes, it is from Nikolai Yasinsky from Russia. Professor Woods, is this list of factors chosen caused presumably by 3D world nature, and we could choose other climatic or non-climatic parameters for classification, or this list is exhaustive?
Okay, the list is not exhaustive. The list was created by starting with a longer list of climatic parameters and then identifying that there was some redundancy. So for example, when we started, we also had a rainfall intensity parameter included. But at the global scale, we found that it did not add much extra information that wasn't already present in the aridity signal. Now, if we were to study something in more detail, so for example, if we were to study flood magnitude, then we might want to reintroduce this information about rainfall intensity, but it would be at a lower level in the hierarchy. I think to some extent, the decision to only put climate variables in and not any catchment attributes is a subjective choice to some extent, but because climate is so important at the global scale, at the moment, it seems like quite a useful choice. I'm still open to evidence that would suggest that we should do something else instead. And I have been having some debates with colleagues about, for example, the importance of maybe drainage density or elevation range as strong, large-scale indicators of hydrological processes. We'll see what the evidence says.
Right, thank you. And you also said that for wet the climate is more important for wet situations, and for dry ones, geology. So perhaps this may also influence.
Yes, I think some of these decisions depend on exactly which question you are trying to answer, which aspect of hydrology you want to think about. And so when I chose at the beginning just 3 climate variables, I was taking a very big picture view and trying not to think about anything in particular. And so you always leave out important details when you try to simplify. But I think if we don't simplify, then no one will listen to us. They will just say, oh, this is too complicated.
Right. Okay, thank you very much. So we move to the next question from Alexander Tarasov from Russia. Professor Woods and Dr. Stein, if I understand, you don't consider altitudinal zonation in the classification. Is it correct? So it refers to the previous one. Can we neglect this factor in the case of hydroclimatic classification?
No, I don't think we can neglect it. And I think it needs to be introduced when we start to think at the catchment scale. Many of the analyses that I produced used very large scale climate data just to divide the world up into different kinds of places. The altitudinal range within a catchment may have significant effect. And for example, maybe it's colder at higher elevations, and so we get snow-driven processes at higher elevations, but not at lower elevations. Now, identifying this and describing this within catchment variability may be important, but it depends. I mean, if you have a catchment where there isn't any snow and there aren't really very strong altitudinal controls on any hydrological process, then maybe we won't need it. I think I don't have a comprehensive answer to this, but I don't think that it belongs right at the very highest part of the hierarchy.
Thank you very much. We move to next question. It's coming from France, from Dr. Mark Ehrlich. Question reads as follows. Could you explain why on the list of topographical attributes, slide 28, the floodplain area is not considered? In the majority of floods, the inundation plains play an important, if not predominant, role.
Okay, so I agree that floodplains and inundation can play an important role in the distribution, the spreading of floodwaters and the distribution of flood velocities. But I'm not convinced that they play a significant role in understanding the flood magnitude, that is, the understanding why the peak discharge is the way that it is. I think to some extent our results may also be influenced by the tendency to study catchments which are not very large. So many of these catchments in the US that we looked at are no more than about 10,000 square kilometers. And at that scale, it may be that the floodplain geometry doesn't really have much influence on the flood peak, because most of the flood peak magnitude is being controlled by the runoff that's generated in the headwaters.
Thank you very much. Next question comes from Tatiana Gubareva from Russia. Hello, Ross. Thank you very much for a very interesting presentation. It is clear that a wide range of characteristics, climatic, hydrological, geomorphological, and many others, are necessary to be used for classification. But what about the methods used in classification procedures? Some slides demonstrate the application of well-known procedures such as cluster analysis and risk curves. But are there any new techniques, methods, statistical similarity metrics? Is there any general practical procedure or an accepted algorithm for classification, or it all depends on the situation, what we classify and what initial information we have? Thank you.
I don't think I'm enough of an expert to give a really good answer to this question. My experience with clustering methods has been that it's required quite a lot of human input to decide what is a sensible number of classes to use. So I don't think there's an ultimate answer. I also think that in some senses, you get out of clustering what you want. You get the number of classes that you ask for. There are some techniques that will try to identify for you how many classes you should have, but I've not found them convincing. I think the most useful thing that's a new technique that we came across is the work that Linus Stein did with accumulated local effects. This is a way of doing sensitivity analysis in order to decide which variables are significant in explaining variability in a data set. And so I'd encourage you, if you're interested in sensitivity analysis, that you take a look at this accumulated local effects idea. So this is in the second paper where Linus Stein is the first author, the one that's under review at the moment.
Thank you very much. We move to the next question from Nikita Turmachov from Russian Federation. Professor Woods, does this classification approach work for short-term or long-term forecasts?
Okay, I think this approach is intended for what I would call, I guess, long-term. It's not intended to produce, for example, a flood forecasting technique that will tell me how big I estimate the river flow to be in 2 days' time. It's not really aimed at questions like that. It's aimed at understanding what drives the long-term hydrological statistics of different locations. So what controls the water balance? Why is it that only 40% of the precipitation becomes runoff in this place, but 60% in this other place?
Right.
It's not confined to just long-term runoff coefficients, but it's confined, I think, to long-term descriptors of typical behavior.
Right. Thank you. I would love to give opportunity for also Professor Gelfand and Professor Kotsoyanis who are present in this talk. If you have any questions, please, you have an opportunity to pose them. Dimitris? Unmute.
Afternoon. No question. Thank you very much.
Thank you, Dimitris. And Professor Gelfand?
Maybe one question. Thank you very much for your presentation. It's very impressive. My question is, what is your opinion, Ross? Should we use different hydrological model performance measures for river basins with different seasonal stream flow regimes? Should we use different performance measures for modeling?
Different performance metrics in different places. Yes, I think so. And I will try to use an example. So well, I guess to some extent, it depends what you want to do with that performance metric. But if you want to compare model performance between two places that are hydrologically very different, maybe you have one catchment which is entirely dominated by snowmelt. So it has a very strong seasonal cycle. And so you build a hydrological model and you assess its performance. Now, if you use something like Nash-Sutcliffe efficiency, you're almost guaranteed to get quite a high score just because it's a regular process. That even terrible models get quite good scores. Whereas if you go to very arid places where the stream flow is very intermittent, even the most sophisticated models we have still tend to score very poorly. So to me, it doesn't really make sense to compare these metrics if we're using something like Nash-Sutcliffe efficiency, which is very widely used. And I think changing to Kling-Gupta efficiencies does not really solve this problem. I think what becomes important is that we think a little bit harder about what is it that we want our model to do, that we don't just unthinkingly adopt a standard metric. I see the value in standardization, but I think everybody using Kling-Gupta efficiency everywhere is not really going to get us very far. We have to think harder about which features of the hydrology it's important for our model to produce. So some kind of hydrological signature which is relevant for that place.
Thank you very much. I fully agree with you.
Okay, thank you very much. To conclude, I would like to pick up the last question, which I haven't posed, and to connect to what has been just said about the utility or usefulness of the approaches we use in hydrology. So the question is, oh, it disappeared from my list. Somebody deleted it. No, it moved to the next page, sorry. So actually this question is from Uganda, from Cornelius Chen. And question is this: I would like to know how one could easily do a stream flow forecast. Perhaps it's not a question based on the material of this lecture, but I would like to connect and maybe expand this question, if I may. And question would be this: in the end, we're interested indeed in saving properties and human lives when we do flood modeling, and so there is a final objective of everything we do. So how would you see this approach you presented to help in our water management efforts?
I think the most useful part at the moment is at the very early stages of any kind of planning or management activity, being able to identify different types of places and being able to say, I expect to have this kind of problem here and this other kind of problem over here. So just for scoping studies, I think it can be useful. And then at a more technical level, I think in the selection of models, I think that from this kind of work and some other work that I didn't cover at all, but which was done by another one of my students, Wouter Knoben, and recently appeared, there is some evidence that different kinds of model structures are more suitable in different places. So I think that this kind of work also potentially has value in selecting appropriate tools. I don't think that it can replace the need to gather local information, but I do think it can provide guidance in what is the set of possibly useful tools on the one hand, and on the other hand, the set of tools which are simply not relevant.
Dr. Ross, thanks a lot. That's really would be great. It's one of your dreams. I would like also to thank you to use the Russian hydrologists, Budiko and Lvovich, I noticed, and maybe more. So it sort of a reference to Russian hydrological school is really great. Thank you very much for doing this. And actually, this school continues, and this Russian hydrological school continues, and this school for young scientists actually is manifestation that this work is going on and being developed further to new heights. Colleagues, I would like to thank all the audience for listening to a very interesting lecture of Professor Woods. Thank you very much. We are applauding all the audience and all to you. Thank you very much. And to your colleague, Ms. Stein, for bringing in new knowledge to the audience. And we will convene in 10 minutes to listen to the lecture of Professor Pomeroy. Thank you very much.
Okay, thank you very much. And thank you for the invitation. I really appreciate it.
Thank you for finding time to give this lecture.